Hey everyone, welcome to a deep dive into a world where colors and shapes collide.
Oh, wow.
Yeah, we're about to uncover this surprising link between graph coloring and aperiodic tilings.
Mhm.
You know those non-repeating patterns that you see sometimes in cool mosaic designs?
Oh, yeah.
Get ready for some serious aha moments because we're going to unpack how these seemingly different concepts are actually deeply connected.
Yeah, it's like finding a hidden pathway between two separate islands. No, on the surface, they look totally different. But underneath, there's this whole interconnected world.
Right.
And we'll be exploring how simple rules about colors and shapes can lead to some incredibly complex structures.
Okay, so our guide for this journey is an academic thesis called Exploring the Parallels Between Graph Coloring and Aperiodic Tilings.
Okay.
Buckle up, because this deep dive is going to take us from the world of maps and colors to the realm of computational power and even real-world quasicrystals.
Wow.
I'm already intrigued.
Let's start by, setting the stage. You've probably seen those brain teaser puzzles where you have to color a map so that no two bordering countries have the same color.
Right.
That's graph coloring in a nutshell.
Right, and the goal is to use the fewest colors possible.
Yeah.
Efficiency is key.
Exactly.
But when we talk about aperiodic tilings, it's a different game altogether. It's not about minimizing. It's about creating these patterns that never repeat no matter how far you extend them.
Exactly. Think of it like tiling a floor with shapes that fit together perfectly, but never create a predictable repeating pattern. And what's fascinating is that both graph coloring and aperiodic tilings rely on satisfying these local constraints,
Okay.
simple rules at the individual level to achieve some desired global property. That's the common thread that ties these concepts together.
Okay, I'm seeing a glimmer of a connection here, but how do we actually bridge the gap between colors on a map and these intricate tiling patterns?
So the thesis makes this brilliant leap by mapping tiling problems onto graph elements. So imagine each tile becomes a vertex in a graph. And the edges represent the rules about which tiles can be placed next to each other.
So we're basically translating those complex tiling patterns into the language of graphs.
Yeah.
That's clever.
Yeah, it opens up a whole new toolbox.
Yeah. We can use graph theory concepts to analyze and understand those complex tiling patterns.
All right, let's talk about these constraints, the rules of the game.
Sure.
In graph coloring, it's simple. No adjacent areas can have the same color.
Right.
But in tilings, it gets much more intricate, right?
Imagine a jigsaw puzzle where each piece has very specific rules about what can touch it. Maybe colors have to match or edges have to line up in a certain way.
Right.
That's what tiling constraints can be like.
Okay, that sounds way more challenging than coloring a map.
Yeah.
So we've got these simple local rules, but they can lead to some pretty mind-blowing global structures. How does the thesis compare those outcomes?
So in graph coloring, those local rules influence something called the chromatic number.
Which is the minimum number of colors needed.
Right.
And in aperiodic tilings, those same kinds of rules determine whether or not we get a non-repeating pattern.
Oh.
So it's not a direct comparison, but the underlying principle is the same. Local constraints drive the emergent global properties.
So it's like those domino chain reactions?
Yes.
One little push sets off this whole cascade of events.
Exactly.
Now, I've heard about these things called Wang tiles, and they sound pretty wild.
Oh,
What's the deal with them?
Wang tiles are like those jigsaw pieces we talked about.
Okay.
Square tiles with colored edges that have to match up perfectly.
Right.
But here's where things get really interesting.
Okay.
Figuring out if a set of Wang tiles can tile the entire plane without any gaps or overlaps, that's a problem that's fundamentally undecidable.
Undecidable, you mean there's no way to know for sure?
Yeah.
Come on, math always has an answer.
Not this time. It means there's no computer program, no algorithm that can give a definitive yes or no answer for all possible sets of Wang tiles. It's a problem that goes beyond the limits of traditional computation.
Whoa. So even with these seemingly simple rules, we're bumping up against the boundaries of what we can know.
Right.
That's pretty heavy stuff for colored tile.
Yeah.
Are there other kinds of tilings that push those boundaries?
Absolutely. Another fascinating type is called substitution tiling. It's like those Russian nesting dolls.
Okay.
Where you start with a big tile and replace it with a pattern of smaller tiles.
Right.
And then those smaller tiles get replaced with even smaller patterns.
Okay.
It's like a fractal pattern built out of tiles.
So you're saying those substitution tilings create those infinitely complex patterns, the kind that never quite repeat?
You got it.
Okay.
And the matching rules in these tilings can get even more intricate. It's not just about adjacency anymore.
Right.
We have to consider colors, patterns, and orientations within those nested patterns.
It's like the constraints themselves are evolving as we go deeper into those substitution layers.
Exactly. And this echoes the complexity that we see in some advanced graph coloring problems. It's amazing how these seemingly simple concepts unfold into such intricate mathematical landscapes.
We've covered so much already, and I'm ready for more. But I think our listener might need a moment to process all these mind-blowing connections before we dive deeper into the world of computational power and real-world quasicrystals.
Okay, ready for more.
Yeah, bring it on.
Let's talk about how computationally complex these concepts can get.
Okay.
Both graph coloring and tiling problems can be incredibly challenging for computers to solve.
Yeah, bring on the computational challenge. How do these problems trip up computers?
Well, remember that chromatic number in graph coloring?
Uh-huh.
The minimum number of colors needed?
Right.
Figuring that out for a large, complex graph?
Okay.
That's what we call an NP-hard problem.
NP-hard. Okay, that sounds like a computer science headache.
Yeah, it means that these problems become exponentially harder to solve as the graph grows. Think about trying to color a map of the entire world with every tiny region needing a different color from its neighbors.
So even with supercomputers, finding the most efficient way to color a giant map could take forever.
Pretty much. And when we jump over to tiling problems, things can get even weirder.
Yeah.
Remember those undecidable Wang tile problems?
Yeah.
Those are NP-hard on steroids.
So some tiling problems are even harder for computers to crack than those NP-hard ones.
Exactly. They fall into a whole different category of computational complexity. It's like hitting a wall where algorithms just can't give us a definitive answer, no matter how much computing power we throw at them.
Wow, so we've got this spectrum of difficulty.
Right.
Graph coloring can be tough, but some tiling problems are just straight up unsolvable by computers.
In a general sense.
In a general sense, that's humbling, to say the least.
Yeah, it really highlights the depth of these seemingly simple concepts. Now I'm curious, how does the thesis visually represent these connections? Are there a lot of diagrams?
It's not a visual extravaganza.
Okay.
But the thesis does a fantastic job of explaining how to map tilings onto graphs, even without relying on a lot of diagrams.
Interesting. So how does that mapping work?
Each tile in a tiling becomes a vertex in a graph.
Oh.
And the edges connecting those vertices represent the rules about which tiles are allowed to touch, just like we talked about earlier.
And those intricate matching rules?
Yeah.
The colors, the patterns, the orientations, are they included in this graph representation?
Absolutely. Those matching rules are represented as labels on the edges of the graph.
Oh, wow.
So you can see even without pictures how a tiling problem morphs into this network of vertices and edges, all governed by those specific matching rules.
So you can almost see the tiling patterns taking shape within that network of connections. Are there any specific examples of tilings where this link to graph coloring becomes super clear?
Definitely the thesis brings up Penrose tiling.
Yeah.
You know those mesmerizing, non-repeating patterns that almost look hypnotic?
Oh, yeah. Penrose tilings, they're usually made with just two shapes.
Right.
Kites and darts that fit together based on specific rules.
And here's the kicker. Because of those complex matching rules, you need at least 4 colors to properly color a Penrose tiling.
Wow.
They're like maps that defy the usual 4-color rule.
It shows how the constraints in tilings directly affect the complexity of graph coloring. The more intricate the tiling rules, the more colors you might need to satisfy the adjacency rules in the corresponding graph.
I love how this all connects. It's still mind-bending to think about how these abstract rules create those stunning visual patterns. Is there a way to make this connection more tangible?
You'll appreciate this. The thesis uses a beautiful metaphor.
Okay.
Imagine those tiles or graph vortices as dancers on a stage.
Okay, I'm already picturing this.
Their choreography represents the constraints dictating how they move and interact.
So the constraints become the steps and movements of the dancers?
Exactly. And the global structure that emerges from all those individual movements, that's our tiling pattern or our colored graph.
It's like those complex synchronized dance routines where each dancer has their part to play and together they create this incredible coordinated spectacle, simple rules, amazing results.
That's it. Whether we're talking about tilings or graph coloring, simple local interactions governed by constraints can lead to breathtaking global patterns. It's a beautiful concept, really.
This deep dive has been full of surprises. Are there any recent discoveries in the world of tilings that have shaken things up and maybe even deepened this connection to graph coloring?
There is. It's the discovery of something called the aperiodic monotile.
Monotile, does that mean, I think it means a single tile that can create a non-repeating pattern?
You got it. It's a single tile shape that can tile the entire plane periodically without any additional matching rules, no colors, no fancy orientations, just one shape, endless non-repeating patterns.
Hold on, that's groundbreaking, one shape. No rules. How does that even work?
It was a huge deal because it solved a long-standing mystery in tiling theory. And guess what? It sparked a ton of new research in graph theory, too.
I bet our graph theorists now on the hunt for the simplest set of rules that can create complex, non-repetitive colorings inspired by this monotile.
Exactly. It's like the monotile threw down the challenge. Find the minimal conditions for complexity in graph coloring. This discovery really pushed the boundaries of what we thought was possible.
Okay, back to the thesis. How does it connect all these incredible concepts? Graph coloring, tilings, computational complexity, even this monotile breakthrough.
It puts them all together under the umbrella of what we call constraint satisfaction problems, or CSPs.
CSP sounds intriguing, but break it down for me.
Think of it as a framework for solving problems, where you have variables each with possible values and constraints that limit how those variables can be assigned. It's like a puzzle with rules.
Okay, so how does this CSP framework apply to graph coloring and tilings?
In graph coloring, the variables are the vertices, the values are the colors, and the constraints are those no same color neighbors rules in tilings. The variables could be the positions of the tiles, the values are the different tile shapes and orientations, and the constraints are those matching rules.
So both graph coloring and tilings can be seen as different flavors of CSPs. That's a neat way to unify these concepts.
It allows us to use powerful algorithms from artificial intelligence and other fields to solve both kinds of problems. It's like finding a master key that unlocks multiple doors.
We've covered so much ground already. Coloring maps, simulating computers, undecidable problems, dancing tiles, even this mind-blowing monotile. It's amazing how these seemingly simple ideas lead to such profound and complex mathematical concepts.
It really is, and the journey's not over yet. We still got to explore those real-world quasicrystals and delve into a few more mathematical connections.
All right, let's do it, but first I think our listener could use a moment to catch their breath. This stuff is mind-expanding. Okay, ready to jump back into those real-world quasicrystals?
Let's do it.
We've talked about all this abstract math, but is there anything in the real world that reflects these, fascinating patterns that we see in a periodic tilings?
There is. It's like the universe itself is playing with these mathematical concepts.
Oh.
You call them quasicrystals.
Quasicrystals. Okay, I've got to hear more about this.
So they're these materials that are ordered but not periodic, just like our periodic tilings. They kind of exhibit patterns that could be predicted by tilings, like the Penrose tiling we talked about earlier.
So those mind-bending Penrose patterns actually exist in nature?
Yes. And get this, they have these rotational symmetries that are impossible in regular, periodic crystals. It's this blend of order and non-repetition that makes them truly unique.
It's like the universe is showing off its math skills.
I know, right?
How does the thesis connect these real-world quasicrystals back to graph theory?
Well, the way atoms arrange themselves in quasicrystals can be modeled using graphs.
Okay.
Atoms become vertices, and the bonds between them become edges.
So we can use graph theory to study the structure of these materials that exhibit those aperiodic patterns.
Yeah.
That's incredible.
It opens up a whole new world of possibilities. We might even be able to use graph coloring techniques to understand the properties of quasicrystals that stem from their non-periodic structure.
I love how this exploration keeps expanding. We've gone from this abstract math to real-world materials that defy our usual understanding of crystal structures.
Right.
Before we wrap up, are there any other mathematical areas that connect to both graph coloring and tilings that we should mention?
The thesis touches on a few more fascinating connections. There's topological graph theory, which explores how the surface a graph is drawn on affects its coloring.
So coloring a map on a sphere is different from coloring a map on a donut.
Exactly. Yeah. Even the famous four-color theorem, which says any map on a plane can be colored with just four colors, changes depending on the surface's topology.
Fascinating. Anything else?
There's also group theory, which uses symmetry to analyze both tilings and graphs.
Whoa.
Think about rotating or flipping a shape if it looks the same after the transformation. That's a symmetry in group theory. Helps us describe those symmetries mathematically.
So symmetry is another tool we can use to unlock the secrets of these structures.
Absolutely. And one last connection, fractals.
Ah, yes, fractals, those mesmerizing patterns that go on forever.
Some tilings and graphs exhibit self-similarity. A key characteristic of fractals. This means parts of the structure resemble the whole structure, just at a smaller scale.
So zoom in or zoom out, and you still see those similar patterns repeating.
Exactly. Studying that self-similarity can give us deeper insights into the complexity of tilings and graphs. It's like finding a hidden code within the code.
Wow, so there's this whole web of interconnected mathematical concepts at play here, all thanks to these seemingly simple ideas of coloring maps and arranging tiles.
Yeah, it's a testament to the beauty and depth of mathematics, and explorations like this remind us that there are always more connections to uncover and more beauty to find.
I don't know about you, but I'm feeling a bit overwhelmed in the best way possible. We've covered so much ground, from the basics of graph coloring and tilings, all the way to quasicrystals, Turing machines, and fractals. I bet our listener is feeling the same way.
They probably are. But before we let them go, let's leave them with a final thought to ponder.
Okay.
If seemingly disparate fields like graph coloring and tilings can have such deep connections, what other hidden links might exist in the vast landscape of mathematics and the world around us?
That's a profound question. It makes you wonder what other unexpected connections are out there just waiting to be discovered.
Exactly, and that's the beauty of exploration and the pursuit of knowledge. There's always more to learn, more to uncover, and more to be amazed by.
This deep dive has been an incredible journey through the interconnected worlds of graph coloring and of periodic tilings. We've explored complex mathematical concepts, encountered mind-bending problems, and glimpsed the beauty of quasicrystals, all thanks to this one academic thesis.
And who would have thought that coloring maps and arranging tiles could lead to such profound insights about computation complexity and the very structure of reality?
It just goes to show that curiosity and a willingness to explore can lead to the most unexpected and rewarding discoveries to our listener. We encourage you to keep exploring, keep questioning, and keep seeking out those hidden connections.
Remember, the world is full of patterns just waiting to be decoded.
Thanks for joining us on this deep dive. Until next time, keep those minds curious and those explorations going.